As we get into chapter 7 gets into some applications of integration. And we've talked about in general what integration is. We said that we have a function that we're integrating, that what we're looking for is the antiderivative. So that's one thing we use the integration for. But most of the applications here are going to be dealing with definite integrals. So remember, if we have the definite integral from a to b of f of x dx, then where we trace that back to was when we were looking for area underneath the curve, and we broke that up into lots of rectangles, and we added the area of those rectangles up, and the way we calculated those areas, where we took the height, which was given by the function, times the width, which we call delta x. We added up those. We took the limit as n went to infinity. And in terms of integration, f of x was still f of x, delta x became dx. So when we're doing a definite integral, we can think about that we're adding up whatever this is. Now, for a lot of the examples, we're going to be adding up basically little rectangles. Sometimes we're going to get into adding up three-dimensional figures like a disc or a shell. Sometimes we're going to add up moments. And when I say moments, that's if we have a pivot and we have a force pushing downward and we have a distance here, we can calculate how much torque is on there. We can add a torques about a figure to calculate different things. So in general, when we're doing a definite integral, we're adding things up. And so far, all the things we've added up have basically been little rectangles with our integral from our f of x and our delta x. And that's still going to be what we're doing in this first section. But as we progress, we might do different variables as well. So the first thing we're going to do in this section is kind of an extension of things we've already done. Instead of finding the area under a single curve, we're going to look at getting the area between two curves. So if I have the function f and the function g, and I want to find the area between those curves from A to B, so I want to find this area here, then notice if we were to find all of this area, and then we were to find this area, then the area between the curves is the yellow area minus this part. We want to get rid of that part because that's not in between them. So the way we would get the area under F, which was the yellow region, is we would integrate F from A to B. The way we would get that green area that we were looked at, that's the area underneath G. So we would integrate from A to B g of x. So we would take the larger one minus the part we don't want, and that would give us the area in between those curves. Now another way of looking at it, erase this real quickly, it is to draw a sample rectangle and say, well, if I want the area in between these two curves, I want to add up all of these little rectangles that go from this curve to that curve. So to get the area of one of those rectangles, we need the length of it times the width. Well, our width is in the x direction, so that's going to be dx. To get the length of this, we would take that distance. Notice that distance from there all the way to the y-axis, that's given by the function f. But that's longer than our sample element. It's this much too long, so we would take away that distance, and that distance is given by g. G is the distance from the x-axis up to that function. So the length of our sample element is f minus g. The width of it is dx. So if we want that area, then we would add up those rectangles from A to B. And those rectangles come from doing f of x minus g of x times d of x. So that's the length times the width. If you do that, then you can get the area between those two curves. Now let's look at the case where one of our curves drops below the x-axis, because in the past we said that if we have a function that's below the x-axis, then when we add up our little rectangles, we get a negative area. Well, let's see if that's still a problem when we're finding the area between two curves. So let's call this F. Let's call this one G. Let's go from A to B. So we want this area in here. So A and B. So we're going to integrate from A to B. And if we look at a sample element, one thing to keep in mind, we're always going to take the top one minus the bottom one. So if we take this distance, that distance is given by f. This distance is given by g, but keep in mind that's negative. Our total distance is this distance plus this distance. Well, let's just look at some sample numbers. If that point has a y value of 4, this one has a y value of -3. If we do the top function minus the bottom one, then our y value here is 4 minus a negative y value. Notice two negatives, make those add up. So as long as we do the top one minus the bottom one, even though this is negative in this section, when we do f minus, the minus and the negative would cancel, so those would add together. So anytime we do f minus g, that's going to take care of your sign, as long as that's the top one minus the bottom one. Now, we have to be careful, because if our functions cross, the top one and bottom one might switch. Let's suppose we have a function f like that, and g like that. And let's find the area between the curves from there to there. And I don't know which one I called. Let's call that one F and G. So if I'm wanting the area between those from A to B, that's that area and that area. So let's call this point x value C. So notice in this section, f is your function that's on top, g is on bottom. In this section, g is on top, f is on bottom. So they swap. So we can't just do from a to b f minus g, because f minus g here would be positive. You think about a sample element. You take your larger minus your smaller, you're going to get a positive. But here, if you do f minus g, you're going to take a small number minus a large number, and you get negative. So what we have to do is we have to break this up into two different intervals. For this sample element, our length is f, the top one, minus g. So for that section, we would integrate from a to c. Our length times our width. And then for this section, we'll integrate from c to b. And if we draw our sample element, the length of this is the top one minus this part. So g minus f. So we always have to be aware of which function's on top, which function's on bottom when we set up our integral. Now, sometimes they'll ask us, they'll give us, let's see, let's draw that part over. They'll give us two functions, and they'll say, find the area between the functions, and they won't tell us what a and b are. They'll just say, find the area in between there. So if we look at that, let's say this function is f and this one is g. Well, these will be our n values. Those will be our a and b. But if those are not just specifically given to us, then notice those 2 points, that those are where f and g are the same. So in order to find the edges of our interval, we'll set our two functions equal to each other, solve, that'll give us those 2 points, and then we'll use those for our lower and upper limits. So let's set up our integral for this one. If we draw a sample element, the length of that, we take the top one minus the bottom one. So in this case, the top one is given by the function g. The bottom is given by f. So the length is g of x minus f of x. And the width is in the x direction, so that's delta x or dx. So let's run through an example of that. Let's suppose we have the function 3x cubed minus x squared minus 10x, and the function g of x equals minus x squared plus 2x. And we want to find the area between those two curves. So let's pull up MathCAD and let's just do a quick sketch of that to save time. So I'm going to pause our video and then get that graph. So let's take a look at our graph. So if we look at our graph, F is the red curve, G is the blue curve. So if we want to find the area in between these two curves, we want to find this area here and this area here. So that's going to actually take two different integrals. Notice there are 1, 2, 3 points of intersection. So we're going to have 3 points, but we can't just set up one integral with 3 different endpoints. So we'll set up one integral between these 2 endpoints, one integral in between these 2. So let's see, let's copy this graph over. So that's our graph. Let's see, our functions were these. So we want to find out the exact x values where those intersect. Now keep in mind, we could do all of this without even knowing what the graph looks like, because we're going to integrate between where f and g are equal. So let's set f equal to g. So 3x cubed minus x squared minus 10x equal to minus x squared plus 2x. We need to get it equal to 0, so if we add x squared to both sides and subtract 2x, we'll get 3x cubed minus x squared plus x squared would cancel. Minus 10x minus 2x will be minus 12x. Both of those have a 3x in common. We can factor out. That factors to a difference of squares. So notice there are 3 solutions when x is 0, when x is 2, and when x is negative 2. Notice 0, 2, and negative 2. So there are 3 points of intersection. Now looking at the graph, knowing that's f and that's g, it's easy to know which one's on top, which one's on bottom. So for this first section, which goes from negative 2 to 0, f is on top, so we're going to do f minus g dx, and then we need to add to it this area. In that section, we go from 0 to 2, and in this section, g is on top, f is on bottom, so we're going to do g minus f, top minus bottom. Now, if we didn't know that, if we didn't have the picture, we could still determine which one was on bottom. We could look and say, okay, let's imagine that we don't have that graph, but we know that we intersect at 0, 2, and negative 2. So those are where we're intersecting. Let's think about which one is on top in this interval, which one's on top here. So let's pick a test point. If we were to pick in this section a test point of 1, in this section g of 1 is minus 1 plus 2, so 1. F of 1 is 3 minus 1, so 2 minus 10 is negative 8. Remember, this is the y value. This one's bigger than that one, so this one's on top and this one's on bottom. If we look at our graph, during this section, g is on top, f is on bottom. Well, if g is on top here and f is on bottom, then by default, it should flip here. But if we weren't sure, we could pick a test point over here. If we put a negative 1 in, negative 1 squared is 1. So negative 1 minus 2, negative 3. If we put a negative 1 into f, negative 1 cubed, that's negative 1 times 3. So negative 3 minus 1, so negative 4. Negative 10 times negative 1 is 10. Negative 4 plus 10 is 6. So in that case, notice f is bigger, so that one's on top. So for this interval, f is on top. So you do f minus g. In this interval, g is on top, so g minus f. Now, for time's sake, I'm not going to go through and do all the integration for you. Hopefully you can do that on your own. But you would just take this function, put in for f, and this function, put in for g, and evaluate that integral, and then do the same thing for the second one. So that's 80–90% of this section. But occasionally we'll be given functions where our input is y. For example, f of y equals y squared. And if we just think about a graph of that, that's basically a parabola that is flipped. If we pick a variety of y's, when y is 0, 0 squared is 0, 1 squared, 2 squared, -1 squared, -2 squared. So we get 0, 0, 1, 1, 4, 2, 1, -1, 4, -2. So that's a parabola like that. So sometimes we might have something like that. Let's suppose we also have a vertical line that goes through here. Let's say that vertical line is x equals 4. And we want to find the area in between there. Notice if we draw our sample element to be vertical, our sample element touches the same function on both ends. This function here is f of y. This is, when I use the term function loosely, it's technically not a function. Doesn't pass the vertical line test, but this part is given by f of y. This part is given by, you could call it g of y, which that's a constant function. Now let's just real quickly, if we have a function f of x equals something, then x is the input, our answer is a y, so f of x and y are basically the same thing. If y is our input, then x is our output, so f of y and x are basically the same thing. Or g of y and x are basically the same thing. So here, drawing a vertical sample element is just not going to cut it. So what we need to do is draw a horizontal sample element. Notice that sample element touches this function here, touches this function here. So let's just look at a sample point. We know that the x here is 4. The x there we got to be 1. So if we want the length of that from here to there is 4. From here to the y-axis is 1. So that length is the difference. 4 minus 1. Notice 4 is the farthest to the right. 1 is the farthest to the left. So when we integrated using a vertical sample element, we did our upper minus our lower function to get the length. If we're doing a horizontal sample element, we do the right minus the left, because that's the larger minus the smaller. So if we want the area of that sample element, It's the right side minus the left side. So our right side is given by G, the left side by F. And then let's look at the width. The width of that is in the y direction. So instead of being delta x or dx, it's delta y or dy. So if I want the area of that rectangle, I take the length times the width, which our width of that rectangle is dy. So we would integrate from here to here. Let's see. Down here in the y direction was -2. Up here in the y direction was +2. The area of one of those rectangles is G minus F dy. So one thing to note, if this is dy, then these are y values. So this is the lower y value, this is the upper y value. When we integrated this way, we were doing dx, so these were x values. So this is the left x, this is the right x. For the next interval, this is the left x, this is the right x. So we're just adding up rectangles in the y direction from the lowest y to the highest y. So in this case, the G is 4, F is y squared dy. So we would just evaluate that integral, and that would give us the area in between those two curves. Now, let's just look at a picture, and let's decide, do we need to integrate with respect to x, or do we need to integrate with respect to y? And that's going to depend on our sample element. So if we're given this function, or that equation, and then this one, then we need to determine, well, do we need to integrate with respect to x or with respect to y? So to determine, we need to think, if we were to draw a sample element, let's just do this. Will that sample element always have one equation as the top, the other equation is the bottom? So notice here, I'm just going to randomly call these F and G for now. F is on top, G is on bottom. But notice if we come over here and draw our vertical rectangle, the top and bottom would touch the same rectangle. So we don't need to integrate with respect to x. So let's see what happens if we draw a horizontal sample element. We draw our sample element here. The right side touches G, the left side touches F, and anywhere we move it to, the same thing's going to happen, at least in respect to one end's going to touch one function, one's going to touch the other. Now, with them intersecting, it could swap which one is which. If we were to come take it and move it down here, now the right function is F and the left one is G, where here the right one was G and the left one was F. So, I mean, that's okay, but we want to make sure that for the whole section, we have one function on one side, another function on the other side. So in this case, we would integrate with respect to y. So if your functions were given as functions of x, then we would want to take those functions, rewrite them as functions in terms of y. So for example, if we had f of x equaled 2y plus 1, let's change that to a function of y. So if we want to change that to a function of y, we want to solve it for x. Functions of x, those are solved for y. Functions of y, those are solved for x. So if this is a function of x, it's solved for y. So if we want to change it, solve it for x, subtract y from both sides, divide both sides by 2. So x we could call f of y, because notice y is our input. Then we would do the same thing for g. So if we did our integral, once we found out where they, and let's not think about this part down here, if we found out where they intersected at A and B, then we would integrate from low to high this one, and we're doing that as a function of y. So the right function minus the left function dy. But again, if those functions were originally in terms of x, we would need to rewrite them as functions in terms of y by solving for x. Okay, so that's what 7.1 deals with.